So, in our last module, we have introduced one logic called temporal logic, and which will be used to specify the property of our system. Now, in this module, we are going to look for verification technique, and mainly we are going to look for a particular verification technique which is known as your model checking. So, in this class, I will just briefly introduce what is model checking and what we can do with the help of model checking. So, I think you might be remembering that in our introductory class, we have slightly introduced about that process of property verification, and we have slightly introduced about the model checking. Now, if you recall back, you will find that in the process of model checking, we are having basically three components. First one is your modeling. So, in case of modeling, what we have to do? We have to give a model of the system, somehow model of the system. With some formalism, we have to define or we have to give the model of our system. If we are going to design a new system, then we are coming up with design, and we are going to represent that design with the help of some model. We will see how we are going to do it. Second component is specification, or we can say that the property to be satisfied by this particular system, or we can say that this is the property that will be satisfied by the model, because we are going to extract out the model of our system. So, in last class we have introduced temporal logic. Temporal logic can be treated as a specification language, and we can use temporal logic to specify our property. And we have discussed a special class of temporal logic which is known as your CTL, computational tree logic. So, basically we will concentrate on this particular logic CTL, and we will see how property can be specified over here. So, one, we have the model of the system, that we have abstract of the model, we represent our property in CTL, or we can give the specification. Then we need some methods or some mechanism by which we can check that this property is indeed true in the model. So, this is the third component which is your verification method. So, in this particular course, we are basically going to look about the model checking technique, which is a verification technique and which is basically property verification technique. So, here in this module, we are going to talk about this particular verification method called model checking. So, this model checking we are going to introduce with the help of one example. First, we will see an example, and then we will see how this example will be model, or how we are going to give the system or the model. Then we will see what are the properties that need to be satisfied this particular example, and how we are going to write those particular property or specification in CTL. Once we have the model, once we have the specification in your CTL, computational tree logic, then we will see that model checking approach, or how this can be verified for that particular model. So, the example that here we are going to discuss about your mutual exclusion. I think all of you know about this particular problem, that it is basically when we are working with the shared resources. So, when concurrent process shares a resource, so we can have several resources. It may be a shared memory, we may have a file, that file may be shared by different users. On the other hand, we may look into the databases also, where the database will be used by different persons or different activities. So, in record also you have to see that record of database will be accessed from different locations. So, in all those cases when we are having the concurrent execution, always we have to look for the consistency of our data. If it is a file, or if it is a database record, or maybe the shared memory. So, whatever data we have over there, it should be consistent. All users should get the similar view of this data. It is not like that I have updated something and that is not reflected for you, then you are not going to get the correct information. So, this is the problem that we have when we are going to use shared resources. So, to have a proper consistency of data, we can use this particular mutual exclusion principle. Okay. So, here in this particular case, we have to see what are the criteria that we need to look for it when we are going to model such type of system. So, in this particular case, first we have to find out what are the criteria that has to be satisfied by this particular design. So, we are talking about that we have to look for those criteria that What are the basically we have to look for that particular portion of code of that particular concurrent processes where they are using this particular shared resources. It may be your file. So, we can have a file, okay. So, it may be used by say several processes or say several users. So, we can say that process 1, so process 3 like that, n different process we are having, and these n processes are going to use this particular file. Okay. So, all those particular processes are having their own code segment. So, in a particular code segment, I think you can think that it is going to access this particular file. So, we have to identify that particular code section. So, two such processes should not access the file simultaneously. That is the restriction we have to say, and we say that we have to identify those particular critical section. We said that the file used by this particular code segment will be treated as our critical section. So, all process may have critical section. So, they should not use this particular file at the same time. Now, by looking into this criteria, we are going to talk about the critical section. When you talk about this mutual exclusion, then we have to see how to model this particular system. Now, we are going to talk about the concurrent processes, going to use some shared resources. So, for that we have to come up with a model. And what will be the specification or what are the specifications that need to be satisfied by this particular model. Okay. So, once we are having the specification, we have to come up with the specification, we have to look for the properties, we will come up with the system model, and what we are going to say, how this we are going to check whether this specification indeed true in this particular system model or not. So, our first task is to come up with a model. Okay. Now, you just see that now what is this particular mutual exclusion. We are considering a simple cases where we are saying that we are having two processes mutual exclusion for shared resources. We are considering only two processes. These two processes are going to access some shared resources. It may be your shared memory, it may be a file, or it may be a database record. So, for that particular cases, what happens, each process can be divided into three different steps. We can say that it is your non-critical and trying T and critical C. So, non-critical and basically it says that the process is in your non-critical region. That means, it is not using any shared resources. So, all process can work in the non-critical region simultaneously. That state T, we are talking about this trying. Basically, we said that now one particular process is trying to enter into the critical region. Basically, it gives the request that it is trying to work with this particular shared resources, and our requirement is like that only one process can use this particular shared resources. When it gets the access to the shared resources, then we say that the process is in your critical section. Okay, that means, now it is accessing this particular shared resources. So, this is critical C we are saying. So, we can say that one particular process can be in any one of these particular three states, N, T or C. N is non-critical region, T is it is trying to enter into the critical section, that means, it is requesting for this particular shared resources, and critical means now process is executing in the critical region, that means, it is working with this particular shared resources. Now, we are talking about two process mutual exclusion. So, we are having two process, now say that I am having process P 1 and I am having process P 2. Now, process P 1 can have in this particular three state, either it was in N 1, T 1 and C 1. Similarly, process 2 can be in three states, it is either in N 2, T 2 and C 2. Now, what are the transition you just see that if it is in the N 1, that means, it is in your non-critical section. Now, at some point of time it may go to the trying state, that means, now it is try to enter into the critical section. Once it is entering into the trying state, that means, now it is going to access the shared resources. Now, if it gains the shared resources, then what happens? It will go into the critical section, that means, it is going to use this particular shared resources exclusively, it is going to use this. Once its job is over, then what will happen? Now, it will come out from critical section to non-critical section, that means, it is going to do the other normal execution. So, this is the transition of our process P 1. Similarly, for process P 2 also we have this particular similar transition. So, N 2 to T 2, T 2 to C 2 and C 2 to N 2. So, these are the possible transition that we have one process P 1 and process P 2. Now, we are going to see these things as an as one system, and for that what we are going to do? The behavior of these two process P 1 and P 2 will be composed together. Generally, we say this is the parallel composition. Now, when we are going to get a composition of this process P 1 and P 2, then we are going to get the total behavior of our system. Now, now we will see what this total behavior will look like. Now, eventually we can come up with such type of finite state machine. Why I am talking about? Already I have said that this is your some sort of your finite state machine. We are having finite number of states and we are having transition amongst them. Now, what are the states? You just see that. First, I am talking about, say, this is given as your N1, N2. What does it mean? It says that the process P 1 is your non-critical section, process N2 is in your non-critical section. So, both are executing, doing their own job, but none of them are using the critical section. Now, when the state is your N1 and N2, then what will happen? At some point of time, process P 1 may look for the shared resources. So, it will go from N1 to T1. So, it is having a transition from N1 to T1. So, we are having the next state in T1 and N2. It is process P 2 is a non-critical section and process P 1 is in your trying section. At the same time, it may happen that now process P 2 may look for that particular shared resources. So, we may have another transition. So, it is from N1 and N2 to N1 to T2. Okay. So, now you just see that initially both are in the non-critical regions. Now, either P 1 try to enter into the critical section. So, it will then the states we are going to get is your N1 T1 N2, and when process P 2 wants to enter into the critical section, then we are going to get the state N1 T2. Now, when it is in your T1 and N2, you just see that either now process P 1 is going to get the shared resources. So, T1 will enter into the critical section and N2 remain in the process P 2 remains in the N2 state. It is in the non-critical section. But it may also happen that now once is trying that process P 1 is trying, similarly process P 2 may also try to enter into the critical section. So, the state we are going to have is your T1 and T2. Now, after some point of time that process these things what you call P 1 will come out from the critical section. So, we are going to have this particular N1 and N2 state. And now, when similarly this part is symmetric to the other part, that it is from T2 it is going to C2, then it will come out and it will go from N1 and N2. Now, when both are trying to enter into a critical section, so one will go to say process P 1 will go into a critical section. So, it will follow this particular part and process P 2 will go into the critical section, then it will follow this particular part and from that it will come to this particular T1 state. So, you just see that with this particular state transition machine, we have basically given the behavior of our system. So, what we have said that mutual exclusion, we say that we are having two process P 1 and P 2, these are the possible states and these are the possible transition. Now, when we are looking into them as a whole, then we are just getting this particular transition behavior. Now, you just see that we are getting a transition behavior and this transition system is going to depict the behavior of our system. Okay. Now, here we are talking about say some state variable. We are saying that we can have for process P 1, we are having N1, T 1 and C 1. For process P 2, we are having N2, T 2 and C 2. Out of that, if you look into this particular behavior, we will say that we are getting 1, 2, 3, 4, 5, 6, 7, 8, total 8 different states and we are having some transition. So, these are the states that we are going to talk about, these are reachable state of my system. So, if my system is going to work correctly or work perfectly, these are the different possibilities that we are having. So, these are the different states that my system can go and we are going to talk about that these are the reachable states. If we are talking about a reachable state, then we may have some other states which may be non-reachable state. So, for this particular example, you can think that what are the total number of states that we may have. Now, you just see that already we have said that we are having N1, T1 and C1 for process P1 and N2, T2, C2. Now, when I talk that in this particular state, I am talking about that this is your N1, N2. That means, both are in your non-critical section. So, these are some state variable, you can say that these are true, basically n1 is true and n2 is true. And what are the status of other 4 variables? We can say that this is not trying to enter into the critical section. So, it is T1 bar, that process P2 is not trying to enter into the critical section. So, it is T2 bar. Similarly, process P1 not in the critical section. So, it is C1 bar, and similarly process P2 is also not in the critical section. So, it is your C2 bar. So, you just see that with this particular combination, basically we are representing these particular states. Okay. Now, in this particular case, so it is basically N1 and N2 are true, that means both the processes are in your non-critical section. So, similarly, T1 is false and T2 is false, they are not trying to enter into the critical section, and C1 and C2 are also false, they are not in the critical section. So, like that, for all those particular states, we can have the behavior of those other variables. Now, in this particular case, we are having total 6 control variable. So, if we are having 6 control variable, what will be a defined possible combination of these particular control variables? We will see that we will get altogether 2 to the power 6 different states, because if we are having n control variables, then we are going to get 2 to the power 6 different states. So, that means my total state space is your 2 to the power 6, okay, which is I think 64. That means, I am going to get 64 different states. This is the total number of states of this particular system, but out of that what will happen? We have seen that only 8 are reachables, others are not reachable, because for a proper system both cannot be in the critical region. That means, C1 and C2 may not, should not be true simultaneously. So, if it is your C1 and C2, then we are having other 4 variables T1, T2 and N1 and 2. So, see these particular 4 variables now have either true and false. So, that means, we can get with 4 variables, we are going to get 16 different states. That means, these 16 different states are not reachable. It is not the proper behavior of our system, and we are going to say that these are the not reachable states. Okay. Like that, some other states will also go out from this particular model, and eventually we are getting only these 8 possible states. Okay. So, these are the reachable states. So, you just see that when we are trying to model our system, depending on the input variables or the control variables, we may have a bigger state space, but all states may not be relevant for us, and we are going to basically concentrate on the reachable states. So, these are the reachable states. Okay. Now, you just see that when we discuss about your temporal logic or say CTL, computational tree logic, we have mentioned that the meaning of this particular CTL is defined over a model. Okay, and what is a model? If you recall back, you will find that this is nothing but some sort of finite state system. We are having finite number of states, we have the transition. So, this is basically behavior of our finite state system, but along with that we are having one additional function which is known as your labeling function. Each state will be labeled with the atomic proposition. If the true atomic proposition is true in a particular state, we are going to label this particular state with the help of this particular atomic proposition. Now, when we are coming up this particular model for mutual exclusion, here we will find that our set of atomic proposition V will be your N1, N2, T1, T2, C1, C2. So, this is the set of atomic proportion that we have in this particular model, and you just see that in this particular state we are marking with N1 and N2. So, what does it mean? That means, this particular atomic proportion N1 is true over here, the atomic proportion N2 is true over here, and other 4 atomic proportion T1, T2, C1, C2 are false at that particular state. Now, you just see that when I am coming up this particular model now very much similar to our Kripke structure that is used for our in CTL to define the meaning of our CTL, computational tree logic formulas. So, now eventually we have come up with this particular Kripke structure. So, for model checking we need a model, we need a specification, Specifications are nothing but the properties that should be satisfied by this particular system, and we need some techniques by which we are going to check whether these particular properties are true in our model or not. So, now the first part we need some model. We have come up with this model of these particular examples of mutual exclusion, and eventually we have found that the way we are representing it, it is going to give us the Kripke structure that is needed to define the meaning of my CTL formula. Okay. So, in last module we have talked about this particular CTL, what is the syntax of CTL and what are the semantics of CTL. Now, we have come up with the model. Now, you just see now, when you are coming to this particular model, so you have come up this particular model and this is very much similar to our Kripke structure. Now, I think now I am writing over here, you just see that AG, EF, N1 and N2, AG, EF, N1 and N2. Now, if you look into this particular expression, I think you can recall that this is very much similar to our CTL formula, and indeed this is a CTL formula. Okay, because you just see that N1 and N2, these are two atomic proposition and they are connected by this particular conjunction. So, N1 and N2 is a CTL formula. Now, this is EF. What is EF? There exists a part in future. So, there exists a part in future N1 and N2. So, I am going to get this is also CTL formula, since this is a CTL formula, EF N1 N2 will be a CTL formula. And before that I am writing AC, that means in all part globally there exists a part in future N1 and N2. That means I can, for creating I can give this particular bracket. So, you see that since this is a CTL formula, so eventually this is a CTL formula. So, now I am writing a CTL formula. Now, what this CTL formula means, you just see that what we can see in sentence, no matter where you are, there is always a way to get to the initial state. So, no matter where you are, that means in the system wherever you are, it hardly makes any difference, no matters, there is always a way, we are going to get a path to get the initial state. Here we are just thinking that this is my initial state. Okay, so, this is why I said that in initial state I am having N1 and N2 must be true. So, no matter where you are, there is always a way to get to the initial state. Now, this is the property that need to be satisfied this particular model. Now, you just see that I am having model. So, this is the model of my system mutual exclusion. This is the specification of the property. One simple specification that I am mentioning over here. So, specification of property. Now, I need some mechanism to check whether this property or this specification is true in this model or not. Okay. And this particular mechanism or technique is known as your model checking. This model checking is a kind of verification technique. It is a kind of verification techniques, and in this class we are going to, or in this course we are going to talk about this particular model checking. So, for model checking, what is our requirement? We need a model of the system. Somehow we have come up with a model which is very much similar to the Kripke structure. We have to represent our property or specification in CTL, then we are going to use model checker, which is basically known as your CTL model checker in this particular case, since we are writing the specification in your CTL formula. So, we are going to look for CTL model checker, and CTL model checker will going to check whether this particular specification is true in this particular model or not. So, this is the way that we are going to look in verification technique, and in this course we are going to talk about model checking, and particularly model checking of our CTL formula, because we are going to write our formula in CTL. Now, when we are talking about this particular mutual exclusion problem of for shared resources, now it should satisfy some of our properties. We are having some requirement, it should fulfill those particular requirement. First, we have to identify what are those particular requirement. So, one requirement we are talking about the safety requirement. What is this safety requirement? It says that only one process to be in its critical section at any time. This is our basic requirement, and say that this is the safety requirement. So, at any point of time only one process will be in its critical section. If two processes are going to remain in the critical section at the same times, both of them are going to manipulate the data, and the manipulation of one process may not be reflected in the other, because it will be overwritten by the other processes. So, this is basically safety property, only one process to be in its critical section at any time. Now, second property we are talking about the liveness. What we are talking about liveness? Whenever any process wants to enter its critical section, it will eventually be permitted to do so. So, we are talking about the liveness. That means, all processes are having equal right to enter into the critical section. So, whenever a process wants to enter into the critical section, that means, it wants to use the shared resources, eventually it should get the permission to use that particular shared resources. So, this is about liveness. If someone is waiting and waiting for long enough time, then we can say that that process is going into starvation. So, it is not desirable. So, the second property is your liveness. Now, say we know that these are the two requirements that we are having. Now, whether if I am having a model, if I say that whether these two properties are satisfied this particular model or not, I think then we will go or we will move into some other domain when we have to look for the natural language processing, because we are representing our requirement in natural language. So, we have to use some formalism or use some formal methods to represent such type of properties. Say like that in my previous example, I am saying that no matter where you are, there is always a way to get to the initial state. So, this is some sort of requirement. I am representing this requirement with the help of this particular CTL formula. So, because this CTL formula having predefined meaning, and we have to use some predefined syntax to write such type of formula. Since meaning is obvious, so now we are going to look for the truth of this particular formula in this particular model. So, like that, these are the two basic properties that must satisfied by my mutual exclusion protocol. So, somehow we have to represent these things in some formal way, and since we know about CTL computational tree logic, we will see how these two will be represented in CTL computational tree logic. Okay. Now, another property is that we are having that non-blocking. A process can always request to enter its critical section. So, this is the non-blocking property. We should not have some criteria that okay, for sometimes we are going to block one process, particular process, that process will not be allowed to enter into the critical section. Then we say that this is some blocking nature. So, we say that our mutual exclusion protocol must satisfy this particular non-blocking property also. The A process can always request to enter its critical section. So, at any point of time, at any moment, any process can give a request to enter into the critical section. We should not put any blocking criteria. And another criteria or another property that must satisfied by this mutual exclusion protocol is no strict sequencing. We should not give any sequence, any strict sequence to that particular process. It is the sequence when you cannot say that process P1 will go into the critical section, then I will allow process P2, then I will allow process P3, then again I will allow process P1 to enter into the critical section, then P2, like that. We should not put any restriction in this particular case. Without any restriction, without any sequencing, they will be allowed to enter into the critical section. It may happen that P1 has entered into the critical section, after some times again P1 may allowed to enter into the critical section. We will not wait for that first P2 must go, then only again P1 will be allowed. So, such type of restriction we are not going to put. So, this is talk about the no strict sequence. So, basically we say that our mutual exclusion, your protocol must satisfy these particular four properties. Now, already I have mentioned that now to be understand it properly, formally we have to specify these things, and here in this particular course we are going to look for the CTL representation of those particular properties, because we are going to look for CTL model checking. Now, the first property, the safety property, you can say that only one process is to be allowed in its critical section. So, we can write this particular CTL formula like that: in all path globally not of C1 and C2. So, if C1 and C2, if it is true, then what will happen? Both the process in the critical section simultaneously. So, not of this must be true. Okay. And where it must be true? In all path globally. That means, in the entire system, in all states along all path this must be true, not of C1 and C2. That is why you are writing this property as in all path globally, not of C1 and C2. Now, you just see that this is a CTL formula, because C1 and C2 is a CTL formula, because C1 C2 is our atomic proposition. So, negation of CTL formula is also a CTL formula, and AG is a temporal CTL operator globally in all paths. So, this is a CTL property. So, we are writing this safety property in CTL formula. Similarly, Leibniz, we are saying that whenever any process wants to enter into critical section, it must be allowed to enter into the critical section. So, we can say that T1 basically it says that the process P1 is trying to enter into the critical section. Then if it is true, then what will happen? In all path in future C1. So, if process P1 is trying to enter into the critical section, then from that particular point wherever you go in all path in future, that process must go into the critical section. So, that is why I am saying that wants to enter its critical section, it will eventually be permitted to enter to do so. So, that is why I am saying that if T1 is true, then it implies that in all path in future we should get a state where C1 is true, and this must be true in all states. So, we are saying that in all path globally this is true. So, this is the way that we are going to write. Now, you just see that this property that I am writing AG T1 implies AF C1. This property is basically related to the process P1, because we are having now two processes, one process P1 and a process P2. Now, similarly, we can write a formula for process P2. So, it will look like or will come up like that AG, if process P2 is trying to enter into the critical section, then in all path in future C2 must be true. So, this is the property related to your process P2. So, process P1 having this particular property, process P2 is having this particular property. But in case of safety, that AG not of C1 and C2, this is for the entire system. So, this is for both process P1 and P2. Okay. So, now just see that we are having safety property and we are having Leibniz property. These two property we have represented with the help of CTL formula. So, these are the two formulas for safety, and this is your Leibniz. Now, we have to check these two property must be true in this particular system. Initially, just I am going to look for this one, say AG not of C1 and C2. So, if you see that we are having 8 possible states, in 8 possible states both C1 and C2 is not true, that means in all states this is true, because here in this particular 4 states C1 and C2 is not true, but here C1 is true and C1 is true, but C2 is false, and in this particular case C2 is true, but C1 is false. So, this AG not of C1 and C2 is true in this particular case. Now, second property what we are talking about, whenever any process wants to enter its critical section, it will eventually be permitted to do so. So, if it is trying to enter into the critical section, in all path in future we should get C1. So, in all path globally T1 implies AF C1. So, in all path globally C1. But if you look into it, here I will be having slight problem, just I will just mention it. Say if you consider that I am in this particular state, the process P1 is trying to enter into the critical section. If I follow this particular path, then it is entering into the critical section, but it is having another path also. Now, you consider this particular path, say from T1 N2 it is going to T1 T2, then it is going for T1 C2. Now, process P2 is entering into the critical section and it is going back. Now, you consider this particular path. Okay. Now, if you consider this particular path, then what will happen? We will find that in this particular path we are not going to get C1, that means process P1 is not entering into the critical section. So, what happens? I will say that this particular formula is false. That means, the model that I have come up over here is not satisfying the Leibniz property, because first one is safety property, we have checked it, safety properties has been satisfied by this one, but when I am coming to this particular Leibniz property, we have seen that it is not satisfying this particular Leibniz property, because we are having one particular part, it will remain in this particular part, and always C2 is entering into this particular critical section. Okay. Now, similarly, we have talked about the non-blocking and we are talking about non-stick sequencing. So, we should not block any process to enter into the critical section and we should not put any strict sequence, that it process must enter in this critical section in some predefined or strict sequence. So, we should not put such type of criteria. So, these two properties also we can represent with the help of CTL formula. So, it says that it is always request to enter into its critical section. So, if the process P1 is in your non-critical section, so there exists a part in next thread, it is T1. Okay. That means, if process P1 is in your non-critical section, from that particular thread we should get at least one part where it is trying to enter into the critical section. That means, we are not blocking wherever you are. If you are in the non-critical section, you are having a provision to try to enter into the critical section. And that strict non-sequencing, no strict sequencing, we can represent this particular property with the help of this particular CTL formula. What it says that since it is we do not put any strict sequence, that means, it is basically says that if it is entering into the critical section, say it is in a critical section, it may happen that after coming out from critical section, it will again allowed to enter into this particular critical section. That is why we are saying that if it is C1 is true and there exists a part, C1 will remain true until this particular property is satisfied, not of C1, that means, C1 will go to not, it will become negation. Along with that, C2 will remain negation. So, C2 will remain false until again C1 becomes false. So, you just see that here we are saying that we are in the C1, we have entered, so you can say that in this particular we are in C1, I can come out from this particular point, we will go to that particular say not of C1, that means, now C1 is false, I am coming out from this particular critical section. Now, what will happen? I should get a path such like that, I can again my system will go to this particular C1, but in none of the state C2 must be true. That means, C2 will remain false, that means, C2 is not entering into the critical section. So, this is the way that I am representing this particular behavior. So, we are saying that not of C2 remains true until again C1 becomes true. So, you just see that again this is a CTL formula, because it is satisfy or it is satisfying the requirement of ours or requirement or syntax of our CTL expression. Okay, you can check it, because we have said that we are having some temporal operator until only we are using over here, and this particular fuchsia also we are using, and we are using this particular part quantifier E and F. Okay. So, this is the way that we are representing this. Now, we have to check whether these properties are true or not. Now, about this particular thing, say AG N1 EX T1, you will find that wherever N1 is there, in next step I am having say T1. Okay, I am having N1, then eventually I am getting T1. So, if it is in N1, that means it is in a non-critical section, there exists a part in next step, it is your T1. Okay. So, it is getting a state where from it is trying to enter into the critical section. So, this behavior is related to your process P1. Similarly, for process P2 also I can write the behavior or property in all part globally. If N2 is true, then it says that there exists a part in next state T2. So, this is the property corresponds to the process P2, and this is the property corresponds to the process P1. Similarly, here what happens, I am saying wherever N1 is true, I am basically concerned about this particular state, and we are going to state that in next step T1 is true. Okay. Because if N1 is false, basically this implication is always going to give me true value true. Okay, we will see this. And this is again the property that we are having, which is related to process P1. Similarly, for process P2, what happens? We can say that this C1 will be replaced by C2 and C2 will be replaced by C1. Then it will, the property will be relevant for your process P2. Again, just I am giving the intuitive idea about it. So, this you can say that this property is again true over here, because we are going to get one particular part where this particular property is true, because this is you can correlate it with the liveness property, because we have said that in this particular part C1 is not getting. So, every time C2 is entering. So, similarly, I can look into this particular part now. Okay. In this particular part, what will happen? Always process P1 is going into this critical section, at no point of time process P2 is going into the critical section. You just see that. That means, in this particular part, I am allowing to enter process P1 to in its critical section. Okay. So, in between process P2 is not getting any chance. That means, we are not following any sequence over here. So, C1 can enter into the critical section for more number of times, and eventually you can say that after some times from here it will come out and it will go to this particular process P2 will go into this process critical section. Now, you just see that here we are talking about this particular mutual exclusion problem, and we have come up with a model, and along with that we have seen this particular 4 property of specification. This is safety, liveness, then no strict sequencing and non-blocking. And out of this particular 4 formula, what happens? We have found that this property is not true in my model. Now, say I am trying to design my this particular critical section or excess of critical section, or basically by mutual exclusion. I have designed it. Now, I have seen that it should satisfy 4 requirements, 4 properties. We have come up with 4 properties. Out of that 4 properties, one is not true. It is not satisfying. Already we have seen it. Now, in that particular case, now what I have to do? As a designer, I should relook my design and try to modify my design in such a way that it is going to satisfy this property. This is the way that we are going to design our system. So, since this property is not true, then I will revisit my design and I will try to check where is the problem, and I will try to fix up that particular bug. Now, after looking into this, what will happen? Now, I can think something like that. So, this is the model that I have come up, and I have seen that this particular property is not true over here. Okay. Because already I have seen that this is the part that we have the problem. That means, in this particular part, what will happen? Process P1 is not getting any chance to enter into this particular critical section C1. Similarly, for process P2, I am having AG, T2 implies AF C2. Since this property is not true, similarly, this property is also not true, because we are going to get this particular part over here, where process P2 is not getting any chance to enter into the critical section. That means, you just see that I am having problem in this particular portion. In my design, I am having some problem over here. It may not be problem with the entire system. So, I will concentrate in this particular part and I try to modify my design. So, in that particular case, what will happen? Somehow I have to break these particular 2 loops. Okay. Now, what will happen in this particular case? Now, I can break this particular 2 loops and I can come up with this particular design. Okay. So, this is the way that we are going to design our system, and we are trying to remove some errors or fault that we may have in our design. Okay. Now, in this particular case, now you just see that what will happen. Now, earlier we have 8 states, now we are getting 9 states. This particular state has been broken into 2 particular states. T1 and T2 has been broken into 2 different states. Okay. So, now in this particular case, what will happen? You just see that now when I am having that T1, it is trying to enter into the T1, then it is entering into your C1, and after that I am coming back to that particular state where N1 and T2. Okay. Now, from here either it can go to T1 and T2, or it can get N1 and C2. That means, it is already entered into this particular critical section. Okay. So, this is the way that you can have, or from here you can say T1 and C2. Now, from here we are going to T1 and N2, and eventually we am coming to this particular C1 either from this direction or from this direction. You just see now, by after breaking this particular 2 loops, I am coming up with a design. In this particular design, you will find that this formula is true over here. Okay. Similarly, that other formula AG T1 implies or T2 implies AF C2 will also be 2. That means, that liveness property will be satisfied over here. Okay. So, this is the way that we are going to what happens after applying this particular verification technique or trying to check for the truth of this particular property. We found that there is some problem. So, now we revisit our design and we have modified it, and we have seen that now this particular design is going to satisfy my liveness property. Now, when it is satisfying my liveness property, then we have to see whether it is not violating my other 3 properties. Okay, indeed, now we can say that other 3 properties are also remain intact over here. Okay, you can recheck it over here, that other 3 properties are true over here. Now, basically you just see that we have starting our design, we have come up with a model M, and after looking for the properties, we try to check whether these properties are true over here or not, and we have found that it is not satisfying some of the property. We have revisit our model and we have come up with this particular model, second model, and in this particular second model, we have seen that at least it is satisfying all those particular 4 specification or 4 properties that we have. Okay. Now, so as for the norms of the QPS structure, we are having slight problem over here that 2 states cannot be marked with the same level. Somehow they have to be different. Now, here I am not talking into this particular internal details, but we can say that instead of this particular 6 states that I am having of the processes, that N1, T1, C1 and N2, T2 and C2, we may have some other internal signals also in the controller. So, these 2 states will be distinguished by some of those particular control signals. Okay. In later point of time, we may look into it, but you can think that they are different because we may have some other control signals which are not relevant with respect to our properties. So, we are not showing the marking of those particular things. Now, what we need next? So, we are having that model, we are having the properties, CTL properties, we are representing our specification with the help of CTL property. Now, we need a mechanism by which we are going to check that those particular properties true in this particular model or not. So, for that we are going to look for a particular model which is known as your model checking. Okay. So, we are going for this particular model checking, and basically here we are going to talk about CTL model checking, because our specification will be represented by CTL formula, and we are going to look for an algorithm by which we are going to check whether a particular CTL formula is true in our model or not. So, we are going to look for model checking algorithms. Now, what is this model checking algorithm? How we can visualize it? You say that given a model M, so we are having a model M, the CTL formula phi. So, we are having a model M, we are having a CTL formula phi, and along with that we are having a state S of S. That means, we are going to look for any state S0 which belong to that set of state S of this particular model, because model M is basically defined by your state of set, transition function and labeling function. Okay. So, this is the critical. So, what is the model checking algorithm? So, model checking algorithm generate answer yes, it will say yes if M S0 models phi, or that means, you can say that phi holds in your M S0 or phi is true in S0. So, that model checking algorithm generate answer yes if phi is true in this particular state S0, or it generate answer no if phi does not hold over here. So, M S0 models phi does not hold, that means, phi is not true in S0. So, this is the way we can look into the model checking algorithm, that we are giving a model M, we are giving a CTL formula phi and one particular state, and we are going to check whether this particular CTL formula is true in this particular state S0 of M or not. So, it is going to say either yes or no. The model checking algorithm may be viewed in the another way also. It says that we are giving a model M and a CTL formula phi. So, we are giving a model M and a CTL formula phi. So, model M again we are saying that it is having state of state, transition relation and labeling function. Now, model checking algorithm we can now view it like that. Model checking algorithm provides all the states of model M which satisfies phi. So, we are giving the entire model M, Now, the model checking algorithm will be run in such a way that it is going to give me the set of states. I can say that S I, S J, S K, like that some states we are having, in which states this particular formula phi is true. So, we can think the model checking algorithm in this particular way also. So, in one case, first case what we are thinking, we are giving a particular state and we are going to check whether phi holds over there or not. In the second case, what we are thinking, that I am giving a model and formula, it will give me all the states where this particular formula is true. So, if we know the method for one, the second one can be always derived. Like that, say if I am giving this particular method, say giving a model M and a formula phi, and it is going to give me all the states where phi is true. Now, if I say that I am giving a model M, formula phi and a particular state say S 0, whether this formula phi holds S 0 or not. So, this method is returning me all the particular states where this particular phi is true. So, I am going to check whether this S 0 is a member of this particular return set or not. If it is a member of this particular return set, then we say that yes, phi is true in S 0. On the other hand, if I know this particular method, then very well I can find out the particular all the states where this particular formula is true, because I am going to run this particular method on each and every steps of the model, and where it is true, it is going to give me those particular steps. So, just see that these are basically complementary to each other. If I know one, the other can be derived. And this model checking algorithm is having another advantage also, or another features also. What happens? It either say it is going to give me either A S if phi is true, and it will going to give me answer no if this phi is false. Okay, that formula is false. Now, when it is no, it is false, generally that model checker generates a counter example also. What is this counter example? With counter example, it give me execution trace. It says that where this particular formula is false. Basically, I am having a giving a model. Okay. So, in this particular model, say I am giving a formula say phi. If phi is not true, then it will say that it is not true in this particular part, then it will give me this particular execution trace, this particular part says that your particular formula is not true in this particular part. Okay. So, that means it is giving a feedback to the designers. Now, when the formula is not true, that means there is some problem with my design. I have to revisit my design and I have to redesign it. But it is that model checker is giving me some clue that my error is somewhere in this particular execution part. So, I can concentrate over here and I can now try to redesign it such a way that this formula becomes true in my model. But when I am trying to basically concentrate on this particular part, some error may occur in some other part also. So, I must be careful about those particular issues also. But model checker is giving me some hints, so that I can quickly try to fix my bugs. Okay. So, this is the issues of our model checking. So, in our next class, we are going to discuss about this particular model checking algorithm. Okay. Now, just look for some question that we are talking about this particular mutual exclusion problem. Now, I am going to look for the liveness properties, checking of this particular liveness property. How I am going to check it, or how we are going to check it. Now, you just see that I am having A G T 1 implies A G C 1. So, this is the CTL formula liveness property that we have given. So, here T 1 is a atomic proposition. So, it is a CTL formula. C 1 is a atomic proposition. So, it is also a CTL formula. Since they are atomic propositions, so we know the labeling function and we know the states where these particular formulas are, or CTL formulas are true. So, from labeling itself, we will say that this is I can say now numbering it. So, this is S 0, S 1, S 2, S 3, S 4, S 5, S 6, S 7. So, T 1 is true in your S 1, S 4 and S 6, S 1, S 4 and S 6, S 1, S 4, S 6. So, T 1 is true over there. Where C 1 is true, you will find that C 1 is true in your S 3 and S 6. Okay. So, These are the CTL formula, and we know that there are truth values on those particular state. Now, what is the next formula that we have to look into it? So, these are atomic proportions. So, these are the CTL formula. Now, the next formula will come as your AG all part globally C1. Since C1 is a your these things what you call C1 is a CTL formula. So, AG C1 is also atomic formula. So, in all part globally, whether it is true or not. So, if you look into it, then you will find that AG C1 is not true over here. So, basically if you look into it, all part globally, you will find that as per our semantics, since C1 is true over here, I can say that all part globally C1 is true over here, all part globally C1 is true over here. Okay. So, these are the issues that we are having. Now, in this particular case, the next CTL formula will come as your T1 implies AG C1. Now, in this particular case, you shall see that if T1 is true, then AG C1 must be true. So, if T1 is false, then obviously this formula is false, because false, we know that in case of implication, if it is your say false and false, it will going to give me true, and false and true also give me is true. So, if T1 is false, then this particular formula is true. So, in this particular case, if I look into that T1 implies AG C1, then it will be true in your S0, because T1 is false. It will be true in your S2, it will be true in your S3, because your T1 is false, it is not there. So, it will be true in your S5, it will be true in your S6, and it will be true in your S7. Okay. So, this is your S7, because it is not true in your S7, I am self marking, because if T1 is false, then only this is true. So, these are the states that we are having 1, 2, 3, 4, 5. In this 5 state, this is true, but now we have to concentrate about these particular 3 states. What will happen to T1 implies AG C1? You just see that T1 is true, then in all part globally C1 must be true. So, already you have seen that in this particular part nowhere I am going to get C1. So, in this particular 3 state, this particular formula is false. Now, we know the labeling of this particular formula, then I can look for the complete formula AG T1 implies AG C1. Now, you just see in this particular case what happens when we are going to look for the truth values of this particular formula, then we must know the truth values of each and every sub formula. So, in our model seeking algorithm, now we are going to do in this particular way that we are going to look for each and every sub formulas. One it is done, then we will look for the main formula. Okay. So, another one you just see that now we are having the second modeling of mutual exclusion, where I have break this particular state T1 and T2 to 2 different state T1 and T2, and I am saying that the second modeling of mutual exclusion is also a oversimplified model. Okay. Why I am saying this is oversimplified? Because you just see that if someone is entering in the critical section, I am saying that after that it is going for non-critical section. Now, how many times it is going to be in this particular critical section? This particular model is not going to depict this particular information. For how long it will be in this particular trying state? If it is trying state, it can go to the C2. Now, how long it will be in this particular critical state C2? So, if I am going to give this particular information, basically I can give some sort of this particular self loop over here like that. That means, it says that it will be remain over here, then it will come out. Now, once I will give such type of self loop, then what will happen? Again it is going to violate my liveness property, because now I will be remain in this particular case. Now, that is why I am saying that this second modeling attempt is oversimplified. But if I will come up with this particular self loop, I will say that it may remain in there for more number of times and it will come out, then what will happen? Still we can try to look for checking those particular property. As such, liveness will be false over here, but what we can do? We can use some fairness of model checking to resolve that issue. To either I can come up with a simplified model, or I can try to depict the entire information where it may not violate some of the property, but what will happen? We are going to use some fairness execution in this particular model, or we are going to use some fairness constraint. What is this fairness? Basically, we will say that you now just see that liveness will be violated if it remains in this particular state forever. But we know that in any system, it will enter into the critical section, it will do its job for required job, which will take some amount of time, and eventually it will come up. That means, we are going to look for a fair execution only. That means, it will not remain over here infinitely. Eventually, it will come out after completion of job, it will come out. That means, what we are going to say, that we are going to look for the fair execution only. That means, what happens? I can think some model. Okay. Okay. So, now you just see that in this particular loop, the model will remain infinitely. Okay. That means, if my system will remain in this particular loop, then I am going to have some bad behaviors. But in fairness, what I am going to say that if my system is correct, I know, then what will happen? Eventually, it is going to come out from this particular loop, and eventually it will follow this particular path. That means, we are going to look for only fair execution. That means, we can somehow omit this particular infinite loops. We are trying to omit this particular part, and we will see that eventually it will come out from this particular loop, and it will going to execute this thing. So, in this particular case, with this particular fairness constraint, we can check for those particular property, because while I am designing my system, it is coming actually. I cannot break this particular loop, because it may be there, but my model checker is giving me some problem, or it is reporting that it is having some error. So, I will say that eventually my system will come out from this thing. So, basically you look to check my property in the fair paths only. So, with fairness constraint, we are going to look for fair paths only. That means, my system will go through the fair paths only. So, like that we can incorporate fairness, and we can go for a model checking on the same system only without breaking this particular loop. Okay. With this, I will stop my lecture today. So, in next class, we are going to look for the model checking algorithm.